Hello and welcome to the screencast where we will introduce the properties of the arcsine function. Let f be the function whose domain is all t values between negative pi over 2 and pi over 2 inclusive and whose outputs are determined by f of t equals the sine of t. We see in this graph that the sine function is the dotted graph and that f of t is only the solid piece of the graph. Note, because it has a different domain, f is not the sine function. Also notice that because the sine function is periodic, it does not pass the horizontal line test on its full domain. And thus the sine function on its full domain does not have an inverse function. However, the graph of f, which is the sine function with a restricted domain, between negative pi over 2 and pi over 2 does pass the horizontal line test. That means we can consider an inverse function for the sine function with a restricted domain. Looking at the graph of the restricted version of the sine function, we see that the domain is all values of t such that t is between negative pi over 2 and pi over 2 inclusive, and that the range is all y values, such that y is between negative 1 and 1 inclusive. In our previous study of inverse functions, we learned that their inputs and outputs are reversed, so we can say that the domain of the inverse of the restricted sine function is negative 1 to 1 inclusive, and the range is negative pi over 2 to pi over 2 inclusive. The restricted version of the sine function that we saw on the previous slide has an inverse function that we call the arcsine function, and we formally define the arcsine function this way. Let y equal f of t equals sine of t be defined on the restricted domain negative pi over 2 to pi over 2 inclusive, and observe that f takes inputs, which are angles between negative pi over 2 and pi over 2, and pairs them with outputs, which are y values on the unit circle from negative 1 to 1. For any real number y that satisfies y values between negative 1 and 1 inclusive, the arcsine of y is the angle t such that t is between negative pi over 2 and pi over 2 inclusive, and such that the sine of t equals y. So we should remember again that the sine of t equals y, t is an angle, and y represents the corresponding y coordinate on the unit circle. That means we can also write t equals the arcsine of y. Notice this also means the output of the arcsine function is t, an angle, and the input of the arcsine function is a y-coordinate on the unit circle. Because the arcsine function is the inverse of the restricted sine function, all the properties of inverses we previously learned will still be true. For example, recall that an inverse function reverses the process of the original function, and that y equals f of t and t equals f inverse of y say the same thing from different perspectives. We know that y equals sine of t means y is the sine of the angle t, and if we change perspective and write the equivalent statements, t equals the arcsine of y, or t equals the inverse sine of y, these mean that t is the angle whose sine is y. Another property of inverses we learned is that any point AB that lies on the graph of f of t equals y corresponds to the point B comma A that lies on the graph of t equals f inverse of y. For example, we know that pi over 2 comma 1 is on the graph of the restricted sine function, and so 1 comma pi over 2 lies on the inverse sine function. Using function notation, we can say that the sine of pi over 2 equals 1, which means 1 is the sine of the angle pi over 2, Or switching perspective, we can also say that pi over 2 equals the arcsine of 1, or the pi over 2 equals the inverse sine of 1, both of which mean that pi over 2 is the angle whose sine value is 1. Later, we'll practice evaluating the arcsine function, always keeping in mind that the arcsine function is defined in relation to the restricted domain, negative pi over 2 to pi over 2 inclusive of the sine function.